Welcome, ladies and gentlemen, to the very first, very fresh episode of 2019 of the Sipkins Physics Corner. Today, I'm going to give you guys a little help with our lab we just did. The conundrum we're in is we have a pullback car that experiences accelerated motion, and we have a tumble buggy that experiences a constant velocity type motion. And your job is to get, we call this the slow-mo chicken lab because we're playing chicken in slow motion. One car is going to start on one side of a meter, the other car is going to start on the other side of a meter stick, and your job is to come up with a model to predict exactly where these cars will collide. Now, that's a challenging lab for your first week of physics. So I wanted to model a problem like this so that you have the mathematical structure in order to solve the lab issue that you have at hand. So here we go. We're going to do a problem just like the one we have, except I just changed up a couple of numbers. But you can use this same concept of solving a system of equations with your kinematic equation in order to solve the issue for this lab. So here we go. We're going to say that our buggy is traveling at a constant speed to the right. So I'm just going to draw a little picture here. Here's a big old buggy. There he is, and he's going to the right at a constant speed of 0.29 meters per second. The buggy starts its journey at a position of x equals 0 meters. So we'll call x initial for the buggy equal to 0 meters. For you viewers that aren't in my class, I teach AP Physics 1, so I'm going to use the same variable structure and subscripts that the College Board uses on the AP Physics 1 equation sheet. All right, so we're going to the right at a constant speed starting from there. It says across the table, a wind-up car, this is the tiny little guy here, the wind-up car starts at a position of x initial equals 2 meters and accelerates from rest to the left at a constant rate of a equals 0.62 meters per second squared. All right, so this is the situation we have. Now, in our lab, we're only a meter apart. For this sample problem, we're 2 meters apart. Again, you can use the same mathematical structure that you're going to see here in order to help you out with your lab. So let's dive into this. What would we do? Well, this kinematic equation dictates where something will be if it's accelerating after a certain amount of time, depending on its initial velocity and where it started. Right? That's what all of these variables mean. So if I take this, I'm going to start with that raw equation, as I like to call it, and I'm going to apply it to each individual object at a time. So let's first do it for the buggy. For the buggy here, we go ahead and write this. See if I can get this in more focused. It's a little blurry. There we go. That's better. For the buggy here, the buggy is moving at a constant speed. And if you're moving at a constant speed, you have zero acceleration. And of course, if you multiply anything by zero, you get zero. So you can see how, because we have no acceleration, this whole term is going to go away for the buggy. Now, the buggy is, of course, moving, so we got to keep that. But we've set the buggy to start at 0 meters. So if I go ahead and plug all these values in, my buggy's velocity is 0.29 meters per second. Don't forget the t, it's right there, plus a position of 0 meters. So I'll kind of write that faded because it's going to go away anyway. So now I have an expression for where is the buggy at any time if it travels along the table at a constant speed. A very straightforward equation. You could also just derive it from v equals the change in x over t and solve for x. Now, I'm going to use the same starting equation, the kinematic equation, but now I'm going to use it for the accelerated car. So let's go ahead and start with the raw equation. Always start with an actual equation. I have some students who are like, I'm just going to come up with my own equation. No, start with a real physics equation and then apply it to whatever context you're in. So let's take a look. Our pullback car is accelerating, but it's accelerating to the left. And now that we're in quantities that have direction, we have to indicate that mathematically. In this case, we're going to make positive to the right, which of course would mean negative would be to the left. And therefore, when I plug this in, our final position of our pullback car is going to be referenced to having a negative acceleration, so 0.62 meters per second squared backwards. All right. Plus, now you notice our pullback buggy, when you do one of these guys, you might remember this from your childhood, when you pull back one of these cars, it starts from rest and then it takes off. All right. So that means that this term for the pullback car is going to go away because our initial velocity in the horizontal direction is going to be 0. So that goes away. Now, the difference here, though, is our initial position is not 0 as it was for the buggy. Our initial position for the pullback car is 2 meters. All right, so let me just kind of simplify this here real quick. If I go ahead and combine these terms together, the 1/2 and the negative 0.62, we're going to get negative 0.31 meters per second squared. Just combine the 1/2 in that term, t squared plus 2 meters. All right, so as you can see, we have 2 equations for our 2 separate cars. And since we've used the same coordinate system, meaning the 0 to the 2 meters and positive to the right, Both of these equations have an unknown x, and they both have an unknown t. And here's where we're going to leverage this idea of the system of equations in order to solve for when or where these cars are going to meet up. Now, since I already have both cars' information in terms of x, here's what you can do. You may remember from math class, if x is equal to some quantity a and x is equal to some quantity b, well, of course, that means then that a is equal to b. All right, that's the transitive property. Well, what does that mean for us? That means that all this stuff on the right side, so for the buggy to be specific, 0.29 meters per second times t, because that quantity is equal to x for the buggy, and because the same x, we're solving for where they hit at the same place at the same time, so we know that the position, both answers are going to come out to be the same, and that both time answers are going to come out to be the same, because we're looking where they collide, where they occupy the same space at the same time. So that's our quantity A is in our little placeholder there. And then this would refer to our quantity B, this little expression that has to do with our accelerated motion of the pullback car. All right, so here we go. Let's drop these in, and you'll see we have the following equation. Now, you may say, Mr. Simpkins, I don't feel like I'm any closer to determining at what point will the two vehicles collide. Well, we've actually done most of the work already. So let's see what we can do with this. If you notice, we have a coefficient t squared, a coefficient t, and a coefficient. And for those of you that are proficient in math course, you might realize that if I subtract the left side quantity over to the right side, what I'm going to end up with is an expression that is in our generic format for the quadratic formula. All right, now remember, this is getting subtracted from both sides, so it's going to be minus 0.29 meters per second times t plus 2 meters. All right, so take a moment, make sure you understand the algebra that happened from here to here. All I did was subtract 0.29 times t from both sides. 0.29 times t from both sides. Okay, so that's how we got to this. Now, some of you are like, oh, sweet, I get to use the quadratic formula. And I'm like, no thanks. Why? Because we can make the calculator do the work for us. So let me show you how you can make the calculator do this math for you instead of having to grind on this really long equation. Anytime you have a quadratic equation and it's set equal to 0, what you can do is get out your calculator, hit the y equals button right there. Y equals, this will come up. If you've been using it in math class, you might have some other functions there. Just go ahead and delete them. And now I'm just going to type in my function, so negative 0.31. Now, ours says t squared. Don't get too upset about that. You'll notice on your calculator there's a button right here. It says x, t, gives you a couple of options. Just go ahead and hit that one. Now it says x, but x is our variable just holding the place of t. So when I type in negative 0.31 x squared, that means negative 0.31 t squared for our equation. Now, you may be asking yourself, what about the units, Mr. Simpkins? I'm just putting there to practice good problem-solving methods. They don't have any numerical impact, so don't get confused and try to go squaring something just because there's a meter per second squared. This is not an operation. This is a unit. Okay, so we got the first term. Now we're going to do minus 0.29t, in this case x, plus r2. Okay, so it wrapped around, but you see how all I did was type this function in the calculator. Now here's the beauty. You hit graph, and it graphs the function for you. There it goes. Now you'll notice there's an intersect over here. What is this showing us? This is showing us our solutions for t when t is whenever the axis crosses, or whenever our function here crosses the 0 or the x-axis here. All right. So this is what happens when you have a quadratic formula. You have the plus and the minus solution. Well, to get an answer for negative time doesn't make sense, so we can automatically rule that one out. And we hope to get an intersection over here through the x-axis that occurs at in a positive value, so that we can go ahead and find that. Now, see this button trace? This allows you to trace along, and you can get pretty close to the answer with that. But the better way to do it is to hit second calc. All right, so I did second. You see the little calc up there, and you're going to go to 0. And what this is going to do is the calculator is going to ask you 3 questions. It's going to say, hey, where's a spot on your function that you just graphed based on our equation? Where is a spot on the function that is to the left of where you expect that it's intersecting at y equals 0? You're going to go ahead and say, hey, this is to the left of that intersection. Then it says right bound. That's asking you where is a place to the right of where you expect it to intersect. I'll hit enter to tell it right there. When it says guess, that just means where do you think, like where's the closest? It doesn't really matter how close you are, as long as you're in between your left and right points, the calculator usually does a fine job figuring it out. And here we go. What it says is where our function intersects at y equals 0, x, or in this case our time, has a value of 2.11 seconds. Okay, so that's how you use your calculator to solve a quadratic equation for. You can use this for all types of questions, not just this type. To review, you type it into y equals, you graph it, you do second calc, give it a left bound, a right bound, and a guess, and it'll spit the answer out for you. Now you're like, well, that's all well and good, Mr. Simpkins, but we still don't have the answer, right? Because the question didn't say when do they meet. It says at what point will they meet. Well, I have good news for you. All this work wasn't for nothing. All right, so we have all of this work. All I'm going to do, I'll scoot down a little bit. All I'm going to do is take this equation that we have for the buggy and plug in our time. Because if it's true that the buggy and the pullback car are at the same place at the same time, I should be able to take our solution for time and plug it into either of these functions. Since this one has more math, I'm going to use the easier function. So let's do a check here. The buggy, where will the buggy be located? What will x be equal to? Oh my goodness, I'm having a big fail day here with the graphite. Where will where will it occur that the buggy is running into our pullback car? I'm going to plug our time in for this t, 2.11 seconds. All right, so the last step here, just grab our calculator, 0.29 times 2.11, and it looks like 0.61. It was 0.6119, so I'll just round it to 0.612 meters. All right, and that's your solution. What does that mean? That means if we go back to our original drawing up here, that means that as the buggy travels consistently, as its consistent speed, this would be like our 1 meter mark right in the middle, right? That means that the buggy will be located at approximately 0.61, somewhere in here probably, 0.61 meters by the time this car is accelerating backwards and running into it. Now the cool thing is we can check that answer because if it works for one, it should work for the other, right? They're supposed to be at the same place at the same time, or in this case, at 2.11 seconds. So I can double check my answer by taking this time and plugging it in to the pullback car function. So let's try that out. 0.31. Again, the units don't have any mathematical consequence. They're just there as a placeholder. All right, but the time that we're going to plug in here is 2.11 seconds because that's the solution we got. So sorry that's a little tiny there, but we're going to do negative 0.31 times, be careful with your parentheses here. You want to make sure you're practicing good order of operations. 2.11 squared, okay, so that's our first term there, plus 2. And we get a really close answer to what we had before. Why is it really close and not exact? Well, because we rounded this number, we rounded this number along the way. So the less rounding you do probably in general, the better. But you see we are at 0.62, which isn't, we're within 1 centimeter of the answer out of 2 meters, which is pretty good if you ask me. It's in 5% certainty range. So that's that's even better than that actually. So that's a very precise answer, and this was just a check to say, hey, is that value close to that value? So there you have it. Now for your buggy and your pullback car lab for the 1 meter chicken or the SloMoChicken lab, all you have to do is take this similar approach. Write an expression based off of your kinematic equation specific to the motion of each car. Use those two expressions to create a combined equation and solve it with a system of equations. Once you get that solution, you can use your calculator along the way to make that easier. Go ahead and plug it back into one of your original expressions, and it will get you the place where your two vehicles will collide. Best of luck. Can't wait to see those SloMoChicken videos. Don't forget to like and subscribe to Simpkins Physics Corner for more awesome AP Physics 1 content throughout the year. Take care.